Something from beyond our solar system is racing toward Jupiter. It's not slowing down, it's not turning around, and in just a matter of weeks, it's going to pass closer to Jupiter than any interstellar visitor we've ever tracked, 5 times closer than it came to Earth. What happens next could rewrite everything we thought we knew about objects that travel between the stars. This is happening in real time, and you're witnessing a moment that has never occurred in recorded human history. We've only confirmed the existence of interstellar objects passing through our solar system a handful of times. Each one has been a fleeting glimpse, a cosmic stranger passing through our neighborhood so quickly that we barely had time to say hello before it was gone. But 3I Atlas, the third interstellar visitor we've ever identified, is different. It's giving us something unprecedented, a second chance. It already passed Earth back in December, and we watched it carefully, learning what we could. But that was just the opening act. The real performance is about to begin at Jupiter, and the proximity is staggering. 5 times closer. Think about what that means for observation, for data collection, for understanding something that came from a place we've never been and may never reach. Stay with me for the next few minutes. In this video, we're going to walk through exactly what's happening right now in the space between Earth and Jupiter, why this encounter matters more than almost any other astronomical event in recent memory, what scientists are scrambling to observe before the window closes, and what the implications are for our understanding of the universe beyond our own star. This isn't just about tracking a comet. This is about learning to read the messages carried by objects that have travelled across the dark ocean between stars, and Jupiter is about to give us the clearest translation we've ever had. When 3I Atlas passed Earth in December, it was moving fast, as all interstellar objects do. These visitors aren't bound by the sun's gravity the way our comets and asteroids are. They're not in orbit. They're on trajectories that take them in, through, and out one-way trips across our corner of the galaxy. The Earth passage was significant. We had multiple spacecraft and telescopes trained on it, capturing data that we'll be analysing for years. But the distance was still measured in millions of kilometres, and while that sounds close in cosmic terms, it's not close enough to see the fine details, the subtle behaviours, the tiny anomalies that tell us what this thing really is and where it came from. Jupiter changes that equation entirely. The numbers are striking. When 3I Atlas passed Earth, the closest approach was roughly at a certain distance that gave us decent observation windows. But when it reaches Jupiter in March, it's going to come 5 times nearer to that massive planet than it came to us. 5 times. That's not a marginal improvement in observation quality. That's a transformation. At that distance, the comet will interact with Jupiter's gravity in ways we can measure with extraordinary precision. It will feel forces that might alter its spin, its trajectory, its outgassing behaviour if it's active, and we'll be watching all of it. If Earth gave us a portrait, Jupiter is going to give us a full-body scan. Why does this matter so much? Because interstellar objects are time capsules. They carry information about other star systems, other planetary formations, other corners of the galaxy that are otherwise completely out of reach. The nearest star system to us is over 4 light-years away. With current technology, sending a probe there would take tens of thousands of years. We're not visiting other star systems anytime soon, but every few years, apparently, other star systems send us visitors. They arrive unannounced, moving at speeds that tell us they're not from around here, and they pass through on trajectories that will eventually take them back out into the void. If we want to learn about the universe beyond our sun, these objects are some of our best teachers. And 3I Atlas is about to give us the most detailed lesson we've ever received. But here's where it gets even more interesting. This isn't just about distance. It's about what happens when an interstellar object encounters the most massive planet in our solar system. Jupiter isn't just big. It's gravitationally dominant in a way that no other planet is. Its influence extends far out into space, warping the paths of anything that comes near. When 3I Atlas enters Jupiter's sphere of influence, everything about its motion will change. The trajectory will bend, the speed will shift. And depending on the angle and the distance, Jupiter could either fling this object out of the solar system faster than it came in, or it could slow it down, altering its path in ways that might keep it visible to us for longer. Scientists call this a gravitational assist or a slingshot effect, and it's been used intentionally to steer spacecraft across the solar system. But when it happens to an interstellar visitor, it's an experiment we didn't design and can't control. We can only observe and learn, and we will be observing. Right now, as I'm speaking and as you're listening, teams of astronomers around the world are coordinating observation schedules, space telescopes are being repositioned, ground-based observatories are reserving time, and at least one spacecraft already orbiting Jupiter Juno, NASA's mission to study the gas giant is potentially in the right place at the right time to catch a glimpse of this visitor as it passes. The logistics are staggering. Tracking something this faint, moving this fast at this distance, requires precision and coordination on a global scale, but the scientific payoff is worth it. We've never had this opportunity before. We may not have it again for a very long time. So what are scientists hoping to learn? Everything. What is this object made of? Where did it come from? Not just in terms of direction, but in terms of stellar environment. How old is it? How long has it been travelling through interstellar space? Does it have a tail, a coma, jets of gas and dust like comets we're familiar with? Or is it inert, more like an asteroid? And here's the question that keeps coming up in the scientific literature, the one that sounds simple but is maddeningly hard to answer. Is this thing natural? That's not a fringe question. It's being asked seriously by credible researchers. And the reason is that 3i Atlas has exhibited some behaviours that don't fit neatly into the models we have for comets or asteroids. We'll dig into those anomalies later in this video, but for now, understand that Jupiter's close encounter will provide data that might finally settle some of those debates or raise entirely new ones. There's a countdown clock ticking here. March 2026 is not far away. In cosmic terms, it's the blink of an eye. In human terms, it's just weeks. And once that closest approach happens, the window starts closing. The comet will move away from Jupiter, fading from view as it continues its journey out of the solar system and back into the interstellar medium. We'll lose it eventually, and when we do, we'll have to wait for the next visitor. There's no replay button in astronomy. This is live. It's happening once, and the data we gather in the next few weeks will be the foundation for decades of research. If you care about space, if you've ever looked up at the night sky and wondered what else is out there, this is your moment to pay attention. This is the cutting edge of discovery, unfolding in real time. And it's not just for scientists. This story belongs to anyone who's curious about the universe, anyone who's ever felt small under the stars and wanted to understand our place in the vastness. So if this sounds like something you want to follow, do me a favour, hit the like button so this story reaches more people who care about it. Subscribe so you don't miss the updates as we get closer to March, and drop a comment telling me what excites you most about this encounter. Are you hoping for answers about where it came from? Are you curious about the technology we're using to track it? Or are you like me, just quietly thrilled that something from another star is passing through our neighbourhood and we get to watch? Let me know. This is a story we're all witnessing together. Now let's get into the details. Let's talk about what just happened when 3i Atlas passed Earth, what we learned, and why that sets the stage for everything that's about to unfold at Jupiter. The months leading up to December 2025 were carefully planned. We knew 3i Atlas was coming. The trajectory had been calculated months in advance. Astronomers had marked their calendars, observatories had scheduled time, and the plan was straightforward. Track the comet through its perihelion in late October, monitor its closest approach to Earth in December, gather as much data as possible, and add to our still thin catalogue of knowledge about interstellar objects. But space has a way of surprising us, even when we think we're prepared. What we learned during those months wasn't just data. It was a preview of mysteries that we're still trying to unravel. The first challenge came during perihelion in late October. As 3i Atlas reached its closest point to the Sun, it was positioned in a way that placed it uncomfortably close to the Sun from Earth's perspective. For ground-based telescopes, that's a nightmare. You can't point a telescope at something near the Sun without risking damage to sensitive instruments and getting overwhelmed by solar glare. It's like trying to spot a firefly next to a searchlight. The comet was there, we knew it was there, but for a critical window of time around closest approach, Earth-based observatories were effectively blind. The comet passed through a zone where the Sun's brightness drowned out everything else. If that had been our only way to observe it, we would have missed some of the most important moments. But we had a secret weapon, one that almost no one outside the space community was paying attention to. The Parker Solar Probe, NASA's mission to study the Sun up close, was in exactly the right place at the right time in late October and early November. This spacecraft wasn't designed to study comets. Its job is to dive closer to the Sun than anything humanity has ever built, measuring solar wind, magnetic fields, and the extreme environment of the inner solar system. But during the critical window from October 18th to November 5th, when Earth's telescopes couldn't see 3i Atlas due to solar glare during perihelion, Parker could. It was already looking toward the Sun, already equipped with instruments that could handle the glare, and it happened to be positioned along the comet's path. So mission controllers took advantage of the opportunity. They aimed Parker's cameras and captured images of 3i Atlas during the very period when it was invisible to everyone else. What did Parker see? A comet behaving mostly as expected, but with details we couldn't have captured from Earth. The tail was visible, the coma, the fuzzy cloud of gas and dust surrounding the nucleus, was active, and the brightness levels matched predictions. But Parker's unique perspective also revealed something subtle: variations in the tail's structure, asymmetries that suggested the comet's rotation and outgassing weren't perfectly uniform. That's not unusual for comets, but for an interstellar comet, every detail matters. These asymmetries could tell us about the nucleus's shape, its composition, how it's been weathered by eons in interstellar space. Parker wasn't supposed to be part of this story, but it became one of the most important observers we had. Then there was Europa Clipper, another spacecraft that had no business observing comets. This mission is designed to study Jupiter's moon Europa, searching for signs of habitability beneath its icy shell. It launched recently and is on its way to the Jupiter system, but in December it was still in the inner solar system, cruising through space on its long journey. When 3i Atlas passed Earth, someone at NASA or JPL had the presence of mind to ask, could Clipper observe it? The spacecraft has ultraviolet instruments designed to detect faint emissions from Europa's thin atmosphere. Could those same instruments see anything interesting in the comet's coma? The answer was yes. Europa Clipper captured ultraviolet observations of 3i Atlas, detecting emissions that are characteristic of water vapor and other volatiles being released from the nucleus as sunlight warms it. This was crucial because it confirmed something we suspected but needed to verify. This interstellar visitor is outgassing, behaving like a comet, not like an inert rock. The UV data showed specific wavelengths associated with molecules we recognize: water, carbon monoxide, perhaps traces of other compounds. It was a snapshot of the comet's chemical fingerprint, and it told us that despite coming from another star system, this object isn't fundamentally alien in its composition. It's made of the same stuff we find in our own comets, which is both reassuring and deeply intriguing. If interstellar comets are similar to our own, what does that tell us about planetary formation across the galaxy? Are the building blocks of solar systems universal? But the real surprise, the observation that made headlines and got scientists talking, came from XMM-Newton, the European Space Agency's X-ray telescope. This observatory orbits Earth and spends its time studying some of the most energetic and exotic phenomena in the universe: black holes, neutron stars, supernova remnants, distant galaxies. It doesn't typically look at comets. Why would it? Comets are cold, relatively inactive compared to the violent processes XMM-Newton usually observes. They don't emit X-rays on their own, but under the right conditions they can. When solar wind, the stream of charged particles flowing out from the sun, interacts with a comet's coma, it can trigger X-ray emissions through a process called charge exchange. It's been observed before in solar system comets, but it's rare, faint, and requires precise timing and positioning to capture. Someone decided to point XMM-Newton at 3e Atlas during its Earth passage, and the gamble paid off. For the first time in history, we captured X-ray images of an interstellar comet. The emissions were faint, exactly as expected, but they were there. And what they revealed was a comet actively interacting with the solar wind. Its coma glowing in X-rays as charged particles collided with the gas and dust surrounding the nucleus. This wasn't just a pretty picture, it was data about the density and composition of the coma, about how the comet is responding to the sun's influence, about the rate at which it's releasing material into space. And because X-ray emissions are sensitive to these interactions, the observations gave us insights that optical telescopes simply can't provide. So by the time 3i Atlas passed Earth and moved beyond our immediate reach, we had observations from 3 very different spacecraft, each capturing a different piece of the puzzle. Parker Solar Probe gave us close-up optical views during the critical window. Europa Clipper provided ultraviolet spectroscopy, revealing chemical composition. XM-Newton delivered X-ray imagery, showing real-time interaction with the solar environment. Together, these observations painted a picture of a comet that is active, volatilic, and responding to the sun in ways we can measure and analyze. It's not a dead rock drifting through space. It's a dynamic object, and it's still evolving as it moves through our solar system. But here's the thing about the Earth passage. It was just the beginning. The data we collected is valuable, but it's limited by distance and observation angles. We got a good look, but not the look we needed to answer the deeper questions. Why does this comet's trajectory seem so precise? Why are some of its outgassing jets oriented in directions that don't quite match standard models? Why does its rotation axis appear to be aligned in a way that some researchers find statistically curious? These are the questions that the Earth passage raised but couldn't fully answer, and that's why Jupiter matters so much. Because in March, when 3i Atlas makes its closest approach to Jupiter, we're not going to be observing from a distance measured in tens of millions of kilometers. We're going to be watching from a front row seat. with instruments that can see details we could only guess at during the Earth flyby. Jupiter is going to act like a magnifying glass, gravitationally and observationally, and everything we learned in December is about to be tested, expanded, and possibly turned upside down. The comet is already on its way. Right now, as you're hearing this, it's travelling through the space between Earth and Jupiter, getting closer to that massive planet with every passing hour. The observations from December are being analysed, papers are being written, models are being refined. But everyone involved knows that the real test is coming. Jupiter is waiting, and so are we. There's a stretch of space between Earth and Jupiter that most people never think about. It's not empty, nothing in the solar system truly is, but it's vast, cold, and mostly uneventful. Spacecraft cross it on their way to the outer planets, taking months or years to make the journey. Asteroids drift through it, remnants of the solar system's formation, quietly orbiting the Sun in predictable patterns. And now, for the first time in recorded history, an interstellar comet is crossing that expanse, and we're tracking it every step of the way. 3i Atlas is moving fast. Interstellar objects don't meander. They're not gravitationally bound to the Sun, so they don't follow the elliptical orbits we're used to seeing from planets, comets, and asteroids. Instead, they follow hyperbolic trajectories, paths that carry them in from interstellar space, around the Sun, and back out again, never to return. The speed required to do this is significant, far faster than the escape velocity needed to leave Earth. This comet is moving at tens of kilometers per second, a pace that seems almost surreal when you think about the distances involved. It's covering the space between Earth and Jupiter in a matter of weeks, a journey that would take a conventional spacecraft months. Right now, in early January 2026, the comet is somewhere in that in-between zone. It's no longer close enough to Earth for casual observation. Ground-based telescopes can still track it, but it's faint, a dim speck moving against the backdrop of stars. The major space telescopes Hubble, potentially the James Webb Space Telescope, could observe it if mission planners allocate the time, but the real focus is shifting to what happens next. The comet is approaching Jupiter's sphere of influence, that vast region of space where the planet's gravity begins to dominate over the Sun's. And once it crosses that threshold, everything changes. Let's talk about what 5 times closer really means. When 3i Atlas passed Earth, the closest approach was at a distance that gave us decent observational opportunities, but it was still far enough that we were seeing the big picture, not the fine details. Imagine trying to read a book from across the room. You can see that it's a book, you can tell roughly how big it is, but you can't read the text. That was Earth. Jupiter is going to bring us close enough to read the text, and maybe even see the footnotes. 5 times closer translates to a dramatically improved resolution in our observations. Telescopes that could barely resolve the comet's nucleus during the Earth passage will be able to see its shape, its surface features if it's active enough to clear away the coma, maybe even individual jets of gas and dust erupting from specific locations. Spectroscopy, the technique we use to determine chemical composition, becomes far more precise at closer distances. We'll be able to detect molecules in the coma that were too faint to identify before. We'll be able to measure the comet's rotation period with greater accuracy, watch how its brightness changes as it spins, and correlate those changes with specific surface features. The data quality doesn't improve linearly with distance, it improves exponentially. 5 times closer is not 5 times better, it's orders of magnitude better. But distance is only part of the story. The other part is what Jupiter does to the comet as it passes. Gravity isn't just an invisible force pulling things together, it's a sculptor, shaping trajectories, bending paths, accelerating and decelerating objects in ways that reveal fundamental properties. When 3i Atlas enters Jupiter's gravitational influence, the planet will start tugging on it. If the comet passes in front of Jupiter from our perspective, the gravity will pull it forward along its trajectory, speeding it up. If it passes behind, the effect will be the opposite, slowing it down. The angle and distance of closest approach determine the magnitude of these changes, and scientists have already calculated what to expect based on the current trajectory. But calculations and observations are 2 different things. We won't truly know how Jupiter affects the comet until we watch it happen in real time. And here's where it gets fascinating. The way Jupiter's gravity affects the comet depends on the comet's mass. If it's a light, fluffy object made mostly of ice and dust, the gravitational interaction will be more pronounced. If it's dense and rocky, the effect will be smaller. By measuring exactly how the trajectory bends and how the speed changes, we can calculate the comet's mass with far more precision than we ever could by observing it from a distance. Mass tells us density. Density tells us composition. Composition tells us where this thing came from and how it formed. It's a chain of deduction that starts with watching how Jupiter's gravity pulls on a visitor from another star. There's also the question of what happens to the comet's activity as it approaches Jupiter. Right now, it's being warmed by the sun, and that warmth is causing ice to sublimate, turn directly from solid to gas, which creates the coma and the tail. But as it moves farther from the sun and closer to Jupiter, the solar heating decreases. Will the comet's activity drop off, or will something else trigger outbursts? Jupiter itself doesn't provide heat the way the sun does, but the gravitational stress as the comet swings past could cause fractures, releasing buried volatiles in sudden jets. We've seen this happen with solar system comets that pass close to the sun. Tidal forces crack the nucleus, and material that was frozen beneath the surface suddenly erupts. Could the same thing happen at Jupiter, even without intense solar heating? It's possible, and if it does, we'll see it. The timeline is tight. The comet will reach closest approach to Jupiter in mid-March. That's the moment of peak observation, the moment when every telescope that can be pointed at it will be locked on, capturing data as fast as the instruments allow. But the encounter isn't a single moment. It's a window that spans several days, during which the comet will be close enough to Jupiter for enhanced observation, and far enough from the sun that solar glare won't interfere the way it did during the Earth passage. This is the sweet spot, the brief period when all the conditions align for the best possible science. And then it will be over. The comet will continue on its trajectory, moving away from Jupiter, away from the sun, and eventually out of the solar system entirely. The window will close, and we'll be left with whatever data we manage to collect. So right now, as 3i Atlas travels through the darkness between Earth and Jupiter, the anticipation is building. Scientists are refining observation plans, coordinating schedules, running simulations to predict what they'll see. The comet doesn't know we're watching, doesn't care about our telescopes and spacecraft. It's just following the path dictated by gravity and momentum, the same path it's been on for who knows how long before it entered our solar system. But for us, this is everything. This is a chance to touch something from beyond, to learn from a traveller that has seen corners of the galaxy we can only imagine. And Jupiter is about to give us the closest look we've ever had. Jupiter is not just another planet. If you grew up learning the order of planets from the Sun, memorizing their names and sizes, you might think of Jupiter as the biggest one, the gas giant with the famous red spot. But that description barely scratches the surface of what Jupiter actually is and what it does. This planet is a gravitational titan, a force of nature that dominates the entire outer solar system and shapes the behaviour of everything that comes near it. When 3i Atlas crosses into Jupiter's domain, it's not just passing another celestial body. It's entering a region of space where the rules change, where gravity bends reality, and where we get to watch interstellar physics play out in real time. Let's start with scale. Jupiter is massive in a way that's hard to grasp. It contains more mass than all the other planets in the solar system combined. If you took every other planet, every moon, every asteroid and comet and merged them into one object, Jupiter would still be bigger. It's not quite big enough to ignite fusion and become a star. It would need to be about 80 times more massive for that. But it's close enough that some astronomers jokingly call it a failed star. That mass translates into gravity, and gravity is everything in space. It's the invisible hand that holds planets in orbit, that flings comets around the sun, that keeps moons locked in their dances and rings spinning in perfect circles. And Jupiter's gravitational reach extends far beyond its cloudy surface. There's a concept in orbital mechanics called the Hill sphere, and it's one of the most important ideas for understanding how gravity works in systems with multiple massive objects. The Hill sphere is the region around a planet where its gravity dominates over the sun's. Inside the Hill sphere, the planet is in charge. Objects within that sphere will orbit the planet, not the sun. Outside it, the sun's gravity takes over. For Earth, the Hill sphere is relatively small, only about 1.5 million kilometers in radius. For Jupiter, it's enormous, extending over 50 million kilometers. That's more than 30 times larger. When 3i Atlas enters Jupiter's Hill sphere, it's crossing into territory where Jupiter's gravity is the dominant force. And that changes everything about how the comet moves. Now, Jupiter isn't going to capture the comet. The comet's velocity is too high, its trajectory too steep. It's going to pass through, not stick around. But even a brief passage through Jupiter's influence has profound effects. Think of it like this. Imagine you're driving a car at high speed down a highway, and as you pass an exit ramp, someone briefly grabs your steering wheel and pulls. You're not going to stop, you're not going to turn around, but your direction will shift. Your speed might change. When you're back in control, you're on a different path than you were before. That's what Jupiter does to objects that pass by. It tugs, it pulls, it redirects. And because gravity is so precisely measurable, we can watch that redirection happen and learn an extraordinary amount from it. One of the key things scientists want to measure during this encounter is the deflection angle, how much Jupiter bends the comet's trajectory. Based on current calculations, the comet is going to come in on one path and leave on a slightly different one. The amount of bending depends on the comet's speed and mass. We already know the speed pretty accurately because we've been tracking the comet's position over time. But mass is harder to determine. From a distance, we can estimate it based on brightness and assumptions about composition, but those are educated guesses. When Jupiter pulls on the comet, the deflection will reveal the true mass. A heavier comet will deflect less. A lighter one will deflect more. It's like using gravity as a scale, weighing the comet by watching how it responds to being pulled. And mass is critical because it tells us what this thing is made of. If the mass is low relative to the size, that suggests a fluffy, porous structure, lots of ice and dust with empty space in between, like a snowball that's been lightly packed. If the mass is higher, that implies density, maybe a rocky core or a more compacted structure. Density gives us clues about where and how the comet formed. Did it form in the outer regions of another star system, where ices dominate? Or did it come from closer in, where rock and metal are more common? These questions can't be answered by looking at the comet. They can only be answered by watching how it moves when a massive planet pulls on it. But Jupiter's influence isn't just about bending trajectories, it's also about stress. Gravity isn't uniform. When you're close to a massive object, the side of you facing that object experiences stronger gravity than the side facing away. This difference creates what's called a tidal force, and it can be powerful enough to literally tear objects apart. You've probably heard of the Roche limit, the distance within which a moon or comet gets shredded by tidal forces, because the gravity pulling on the near side is so much stronger than the gravity on the far side that the object can't hold itself together. Jupiter's Roche limit is well inside the orbit of its innermost moons. 3I Atlas isn't going to get that close, so it's not going to disintegrate, but it will feel tidal stress, and that stress could trigger activity. Imagine the comet's nucleus as a rubble pile, a loose collection of icy chunks held together by weak gravity and frozen bonds. As it approaches Jupiter, the tidal stress pulls on it unevenly, creating tension. Cracks might open. Buried pockets of volatile material gases that have been frozen for eons might suddenly be exposed to vacuum and erupt as jets. We've seen this happen before with solar system comets. Some comets brighten suddenly when they're near the sun, not because of increased heating, but because tidal or rotational stress fractures the surface and releases trapped gas. If 3I Atlas does the same thing near Jupiter, it would be a spectacular confirmation that interstellar comets respond to gravitational stress just like our own comets do, and it would give us a chance to study the interior composition. Because whatever comes out in those jets is material that was previously hidden. There's also the Slingshot effect, which is something NASA and other space agencies use deliberately when sending spacecraft to the outer planets. When a spacecraft approaches a planet at the right angle and speed, it can steal a tiny bit of the planet's orbital momentum and convert that into velocity. From the planet's perspective, nothing changes. Jupiter is so massive that losing a bit of momentum to a passing spacecraft is like an ocean liner being slowed down by a mosquito. But for the spacecraft, or in this case the comet, the effect is significant. 3I Atlas is going to interact with Jupiter's gravity in a way that will either speed it up or slow it down, depending on the geometry of the encounter. If it speeds up, it will leave the solar system faster than it would have otherwise. If it slows down, it will linger longer, giving us more time to observe it as it heads outward. Either way, the change in velocity is measurable, and it's one more piece of data that tells us about the comet's mass and trajectory. Why does all this matter? Because Jupiter is rare. There are only a handful of planets in our solar system, and only one with this kind of gravitational dominance. Most interstellar objects that pass through don't come anywhere near Jupiter. They pass through the inner solar system, maybe swing around the Sun, and then head back out without interacting with any of the major planets. 3I Atlas is different. Its trajectory happens to carry it close to Jupiter, close enough that the interaction is scientifically meaningful. This is an opportunity we didn't plan for and can't replicate. It's a natural experiment set up by the universe, and all we have to do is watch and measure, and that's exactly what we're going to do. Over the next few weeks, as the comet closes in on Jupiter, observation campaigns are ramping up. Ground-based telescopes are scheduling time. Space telescopes are being repositioned, and at Jupiter itself there's a spacecraft already in orbit, one that was designed to study the planet but might just get a chance to observe the comet as well. Juno, NASA's mission to Jupiter, is in a unique position. It's already there, circling the planet, equipped with cameras and instruments that could potentially capture images of 3I Atlas as it makes its closest approach. Whether that happens depends on timing, positioning, and mission priorities. But the possibility is real. Imagine that a spacecraft at Jupiter, photographing an interstellar visitor. It would be one of the most iconic moments in space exploration history. Jupiter changes everything, because it's not just a passive backdrop for this encounter, it's an active participant, a cosmic laboratory where gravity, motion, and time interact in ways that reveal truths we can't access any other way. And for the next few weeks, that laboratory is open, and we have front row seats. Tracking an interstellar comet isn't like tracking an airplane or even a satellite. You can't just look up and see it. You can't point any random telescope at the sky and expect to catch a glimpse. These objects are faint, incredibly faint, because they're small and far away. 3I Atlas, even at its brightest, is barely visible through professional telescopes. To the naked eye, it's invisible. To amateur equipment, it's at best a smudge that might not even show up in a photograph. Observing it requires precision, coordination, and the kind of technology that most people will never interact with. Fortunately, we have that technology, and the people operating it are some of the best in the world at what they do. Let's start with the obvious. Ground-based observatories. These are the workhorses of astronomy, the big telescopes perched on mountaintops in remote locations where the air is clear and the light pollution is minimal. Places like Mauna Kea in Hawaii, the Atacama Desert in Chile, the Canary Islands off the coast of Africa. These telescopes have been tracking 3I Atlas since it was first identified, calculating its trajectory, measuring its brightness, capturing spectra to determine what it's made of. They'll continue to play a role as the comet approaches Jupiter, providing continuous monitoring and filling in gaps when space-based assets aren't available. But ground-based observation has limits. The atmosphere distorts light, blurring images and scattering wavelengths. Weather can shut down observations entirely, and there are parts of the sky that ground telescopes simply can't see depending on the time of year and the observer's latitude. For the best possible data, you need to get above the atmosphere, and that means space telescopes. Hubble is the name everyone knows. It's been in orbit for over 3 decades, capturing some of the most iconic images in the history of astronomy. Galaxies, nebulae, supernovae, exoplanets. Hubble has seen it all. And yes, Hubble can observe comets, including interstellar ones. In fact, Hubble observed the first confirmed interstellar object, Oumuamua, back when it passed through in 2017, and it observed the second one, Borisov, in 2019. If NASA allocates observing time, Hubble could add 3I Atlas to that list. The advantage of Hubble is its resolution and its ability to capture ultraviolet wavelengths that don't make it through Earth's atmosphere. UV observations are crucial for detecting certain molecules in the comet's coma, especially water vapor and hydroxyl radicals, which are indicators of how much ice is sublimating as the comet is heated by the sun. Then there's the James Webb Space Telescope, the most powerful observatory ever launched. Webb is designed for infrared observation, peering through dust and detecting heat signatures that visible light telescopes miss entirely. It's been used primarily for studying distant galaxies, exoplanet atmospheres, and the early universe, but it's also capable of observing objects in our own solar system. Whether Webb will be tasked with observing 3I Atlas depends on competing priorities. Telescope time is precious and heavily contested, but if it does, the data will be extraordinary. Infrared observations can reveal the temperature distribution across the comet's surface, detect molecules that don't emit strongly invisible or UV light, and possibly even see through the coma to image the nucleus directly. That's something no other telescope can do. But the real wildcard, the observation that has everyone talking, is Juno. NASA's Juno spacecraft has been orbiting Jupiter since 2016, studying the planet's atmosphere, magnetic field, and interior structure. Its mission has been extended multiple times because the science it's producing is so valuable, and it's currently in an orbit that takes it swooping close to Jupiter's cloud tops before swinging back out into space. Juno wasn't designed to observe comets. Its cameras and instruments are optimized for studying a gas giant, not a tiny icy visitor from another star. But sometimes, the universe gives you opportunities you didn't plan for, and this might be one of them. Researchers have calculated Juno's orbit and compared it to the predicted path of 3I Atlas, and the alignment is tantalizing. Depending on the exact timing of the comet's closest approach and where Juno is in its orbit at that moment, there's a chance, not a guarantee, but a real chance that Juno could observe the comet as it passes. The spacecraft has a visible light camera called JunoCam, which has captured stunning images of Jupiter's poles, storms, and atmospheric bands. Could JunoCam photograph an interstellar comet? Theoretically, yes. The challenge is that comets are faint and move quickly, so capturing a clear image would require precise timing and possibly some creative reprogramming of the camera's settings. But if it works, if Juno manages to catch even a single image of 3I Atlas against the backdrop of Jupiter, it would be historic. We've never had a spacecraft at one planet photograph an interstellar visitor. The closest we've come was when New Horizons, on its way to Pluto, imaged a few asteroids as it flew past. This would be different. This would be a spacecraft at Jupiter, in orbit, capturing an object that came from light years away. NASA hasn't officially confirmed whether they'll attempt this observation. Mission priorities are complex, and every command sent to Juno has to be carefully balanced against the spacecraft's primary science objectives. But the possibility is being discussed, and the scientific community is hopeful. Even if Juno doesn't image the comet directly, its instruments might detect changes in Jupiter's magnetosphere or radiation environment as the comet passes through. Comets carry their own magnetic fields, embedded in the plasma surrounding the nucleus, and when those fields interact with a planet's magnetosphere, interesting things can happen. It's a long shot, but it's the kind of long shot that makes space exploration exciting. Beyond the big names, there are other assets in play. The European Space Agency's XMM-Newton, which already made history by capturing X-ray images of the comet during its Earth passage, could observe it again if the timing and position allow. Other space telescopes, including those focused on specific wavelengths like gamma rays or extreme ultraviolet, might be tasked with looking for unexpected emissions. And then there are the radar facilities, the big dishes like Arecibo's gone, collapsed in 2020. But other radar systems like the Goldstone Deep Space Network dishes and the Green Bank Telescope could potentially bounce radar signals off the comet if it gets close enough and if the geometry is right. Radar observations can measure the nucleus's size and shape with extraordinary precision, even if the comet is too faint for optical telescopes to resolve. The coordination required to pull all this off is staggering. Observing campaigns involve multiple observatories across different continents and different space agencies, all scheduling time and sharing data. There are planning meetings, teleconferences, emails flying back and forth between scientists who specialize in different aspects of cometary science. Some are focused on composition, analyzing spectra to identify molecules. Others are studying dynamics, tracking how the orbit changes and what that reveals about mass and density. Still others are working on modeling, running simulations to predict what the comet will do as it approaches Jupiter, and comparing those predictions to observations. It's a massive collaborative effort, and it's all happening in real time, with a deadline that can't be moved. March is coming whether we're ready or not. And then there's the challenge of the comet itself. Even with all this technology, 3I Atlas is not an easy target. It's faint, which means long exposure times and sensitive detectors. It's moving fast, which means telescopes have to track it precisely, or the image will blur, and it's far away, which means even the best telescopes are working at the limits of their resolution. Every observation is a technical challenge, and not every attempt will succeed. There will be cloudy nights that ruin ground-based observations. There will be scheduling conflicts that prevent space telescopes from observing at the optimal time. There will be data that comes back noisy or incomplete. That's just the reality of observational astronomy. But even with all those challenges, the sheer number of eyes on this comet means that we're going to get data. A lot of it. And when it's all compiled and analysed, we're going to understand 3I Atlas better than we've understood any interstellar object that's come before it. Because this isn't just about seeing the comet, it's about seeing it from multiple angles, at multiple wavelengths, over an extended period of time. It's about capturing not just snapshots, but a story, a narrative of how this object moves through space and responds to the forces acting on it. And the closer we get to March, the clearer that story becomes. Science is built on observation, but observation without interpretation is just data. The real work begins when you try to make sense of what you're seeing. When you ask why something behaves the way it does, and what that behavior reveals about the underlying nature of the object. Most of the time, the answers fit comfortably within existing theories. Comets behave like comets. Asteroids behave like asteroids. The universe follows rules we've spent centuries figuring out. But every once in a while, something comes along that doesn't quite fit, that raises questions we weren't expecting, and that's when science gets interesting. 3I Atlas is one of those things. Let's be very clear about what we mean by anomalies. In science, An anomaly is an observation that doesn't match predictions based on current models. It doesn't mean the observation is wrong, and it doesn't mean the models are completely broken. It just means there's a gap between expectation and reality, and that gap is worth investigating. Sometimes anomalies turn out to be measurement errors or misunderstandings. Sometimes they point to new physics or chemistry, and sometimes they're just reminders that the universe is more complicated than our models give it credit for. 3i Atlas has exhibited several behaviours that qualify as anomalies, and scientists are taking them seriously. The first anomaly involves the comet's trajectory. When you calculate the path of an object through space, you account for gravity, primarily the sun's gravity, but also the gravitational influence of planets if the object passes close to them. For most comets and asteroids, those calculations are straightforward. You plug in the position, velocity and mass, and you get a trajectory. But 3i Atlas's trajectory has a level of precision that's unusual. It's not just heading vaguely toward Jupiter, it's heading almost exactly toward Jupiter, as if the encounter was planned. Now, trajectories can look precise due to pure chance. Space is big, but it's not infinite, and sometimes objects just happen to be on paths that lead to interesting encounters. But when you run the statistics, when you calculate how likely it is for an interstellar object entering the solar system at a random angle and speed to end up on a trajectory that brings it this close to Jupiter, the probability is low. Not impossible, but low enough to make you wonder. Does that mean the trajectory isn't natural? Not necessarily, but it does mean we should look carefully at other factors that might explain it. Could there be non-gravitational forces at play? Comets don't move purely under gravity. When they outgas, when ice on the surface turns to vapour and jets away, that gas acts like a tiny rocket engine, pushing the comet in the opposite direction. These non-gravitational forces are well understood and can be measured by tracking how a comet's orbit deviates from purely gravitational predictions. For 3i Atlas, scientists have attempted to model the non-gravitational forces based on the outgassing observed during the Earth passage, and the models work to a point. But there are small discrepancies, tiny deviations that aren't fully explained by the gas jets we can see. Maybe there are jets we can't see, oriented in directions that don't produce visible tails. Maybe the comet's rotation is more complex than simple models assume, or maybe there's something else going on. The second anomaly is related to those jets. Comets typically outgaze from the side facing the sun because that's where the heating is strongest. You heat ice, it turns to vapour, the vapour escapes, and you get a coma and a tail pointing away from the sun. Simple, predictable. But 3i Atlas has shown outgassing activity that doesn't perfectly align with that model. Some of the jets appear to be oriented at angles that don't correspond to the sun's direction. This could be explained by the shape of the nucleus. Maybe there are areas that are more reflective or more insulated, creating localized heating patterns. Or it could be due to the comet's rotation, which causes different parts of the surface to face the sun at different times, creating jets that appear to point in odd directions when you're looking at a snapshot. But some researchers have noted that the jet orientations seem more consistent than random rotation would predict, as if there's some underlying structure or pattern to the outgassing. Then there's the rotation itself, which brings us to the third anomaly. Most comets tumble chaotically. They're irregularly shaped, they've been battered by impacts and thermal stress over billions of years, and their rotation is complex, often spinning around multiple axes at once. Measuring a comet's rotation period can be tricky because of this complexity. You watch how the brightness changes over time, which tells you how the surface features are rotating into and out of view, and you try to figure out the spin rate and axis orientation. For 3i Atlas, the rotation measurements have been puzzling. Some observations suggest a relatively short rotation period, a few hours, which would make it similar to other comets. But when you dig into the details, the rotation axis seems to be unusually stable and aligned in a way that some researchers find curious. Avi Loeb, a prominent astronomer at Harvard, has pointed out that the axis alignment is statistically uncommon if you assume random orientation. Again, uncommon doesn't mean impossible, but it's another data point that doesn't quite fit the expectation. Now, let's talk about how these anomalies are being interpreted, because this is where things get contentious. In mainstream astronomy, the default assumption when encountering something unusual is to exhaust all natural explanations before considering anything exotic. That's a good scientific principle. Most anomalies turn out to have mundane explanations once you gather enough data or refine your models. So when faced with 3i Atlas's odd trajectory, jet orientations and rotation, the first instinct is to assume we're dealing with a natural comet that just happens to have unusual properties due to its history, composition, or structure. Maybe it formed in a region of another star system where conditions were different. Maybe it's made of materials we don't commonly see in solar system comets. Maybe it's been shaped by eons of radiation and micrometeorite impacts in interstellar space, giving it properties that surprise us. But there's another perspective, and it's worth discussing even if it's controversial. Avi Loeb, who led the Galileo project and has been studying interstellar objects extensively, has raised the question of whether some of these anomalies could indicate something other than a natural comet. He's not claiming that 3I Atlas is artificial. He's saying that the observations are unusual enough that we should consider all possibilities, including the possibility that this object has characteristics inconsistent with a purely natural origin. That's a careful, measured way of asking a question that sounds wild when you strip away the nuance. Could this be technology? Could it be a probe or artifact from another civilization? Most astronomers say no. They point out that every anomaly observed so far has plausible natural explanations, even if those explanations require refining our models or invoking less common scenarios. The trajectory precision could be coincidence, or the result of non-gravitational forces we haven't fully characterized. The jet orientations could be due to surface topology or rotation complexity. The rotation axis alignment could be a selection effect, maybe we're only noticing it because we're looking closely, and other comets would show similar patterns if we studied them as intensely. These are reasonable counter-arguments, and they're backed by the scientific mainstream. But Loeb's point isn't that we should immediately jump to the artificial hypothesis, it's that we should keep it on the table as a possibility to be tested, not dismissed out of hand. Science advances when we're willing to question assumptions and look for evidence that could falsify our hypotheses. If 3I Atlas is a natural comet, then close observation during the Jupiter encounter should reveal behaviours consistent with that outgassing driven by solar heating, trajectory changes driven by gravity and gas jets, rotation, and structural properties consistent with ice and rock. If, on the other hand, there are additional anomalies that can't be explained by natural processes, then we have a more interesting problem. And the only way to know is to observe carefully, measure precisely, and let the data speak. Here's where the Jupiter encounter becomes absolutely critical. Everything we've talked about so far, the trajectory precision, the jet orientations, the rotation anomalies, has been observed from a distance with limited resolution and relatively few data points. March is going to change that. When the comet passes Jupiter, we'll be watching it closer and with better instruments than ever before. If there are non-gravitational forces affecting the trajectory, we'll measure them precisely as Jupiter's gravity amplifies their effects. If the jets are truly anomalous, we'll see them in high resolution and be able to correlate them with surface features. If the rotation is unusual, we'll track it continuously over multiple periods and determine whether the axis orientation holds or changes. In other words, the Jupiter encounter is a test. It's a natural experiment that will either confirm that 3I Atlas is a comet, behaving within the range of expected but unusual properties, or it will deepen the mystery. And let's be honest, mysteries are what keep people engaged with science. The idea that we might be observing something we don't fully understand, something that challenges our assumptions, is thrilling. It's why people tune in to watch rocket launches and telescope discoveries. It's why space exploration captures imaginations in a way that few other endeavours do. We're not just looking at rocks and ice. We're asking questions about where we came from, whether we're alone, what else is out there in the vastness. 3I Atlas might be a completely ordinary interstellar comet that just happens to have a few quirks, or it might be something more interesting. The only way to find out is to keep watching, and that's exactly what the scientific community is doing. Papers are being written, data is being analysed, telescopes are being scheduled. There's healthy debate, which is how science should work. Some researchers think the anomalies are overstated or explainable with better models. Others think they're genuinely intriguing and worth deeper investigation. Both sides agree on one thing. The Jupiter encounter is going to provide the data needed to move the conversation forward. Whatever 3I Atlas is, we're about to learn more about it than we ever have before. And in a few weeks, when that data starts coming in, we'll begin to see whether this visitor from another star is just another comet or something that rewrites what we thought we knew about interstellar objects. Because at the end of the day, that's what science is about. Not clinging to comfortable explanations, but following the evidence wherever it leads, even if it leads somewhere unexpected. And right now, the evidence is leading us to Jupiter. March is not a particularly special month in most contexts. It's the transition between winter and spring in the Northern Hemisphere, a time when the weather starts warming and days get longer. But in the history of space exploration and astronomical observation, March 2026 is going to stand out. It's the month when an object from another star system makes its closest approach to the largest planet in ours, and when decades of preparation, technology, and curiosity converge into a brief window of discovery that we might never experience again in our lifetimes. The timeline is precise. Based on current trajectory calculations, 3i Atlas will reach its closest point to Jupiter in mid-March. The exact date and time depend on final refinements as more observations come in, but the window is narrow, a matter of days at most. During that window, the comet will be at its minimum distance from Jupiter, within the planet's Hill sphere, fully under the influence of that enormous gravitational pull. That's when observation conditions are at their peak. That's when every telescope that can be brought to bear on the comet will be watching, recording, measuring, and that's when we'll see things that might not make sense until we've had months or years to analyse them. What do scientists expect to see? Let's start with the obvious: changes in the comet's brightness. As it approaches Jupiter, the comet will be farther from the Sun than it was during the Earth passage, which means less solar heating. Under normal circumstances, that would lead to decreased activity, less outgassing, a dimmer coma, a shorter tail. But Jupiter's gravity introduces complications. Tidal forces could stress the nucleus, potentially triggering outbursts as buried volatiles are suddenly exposed. If that happens, we'll see a sudden brightening, possibly accompanied by changes in the tail's structure or the appearance of new jets. Alternatively, if the comet is relatively inert or if its surface is heavily depleted of volatiles, we might not see much change at all. The brightness behaviour will tell us about the comet's structural integrity and how much active material it still contains. Then there's the trajectory. This is where the physics gets precise. As the comet enters Jupiter's gravitational influence, its path will start to curve. The amount of curvature depends on the comet's speed, its distance from Jupiter at closest approach, and its mass. We know the first two factors fairly well, so measuring the curvature allows us to calculate the third. This is gravitational weighing at its finest. The deflection angle, the difference between the comet's incoming trajectory and its outgoing trajectory, will be measured in fractions of a degree, and those fractions will translate into mass estimates with error bars far smaller than anything we could achieve through other methods. If the mass turns out to be lower than expected, it suggests a porous ichoric structure. If it's higher, that implies density, possibly a rocky core or a compacted interior. Either way, we'll know. The rotation period is another observable that will come into sharp focus during the encounter. Ground-based telescopes have been tracking the comet's brightness variations over time, which reflect how quickly it's spinning and how uniform its surface is. But those observations have been limited by the comet's faintness and the difficulty of getting continuous coverage. During the Jupiter encounter, the comet will be bright enough and well positioned enough that multiple observatories can monitor it continuously over several rotations. That will allow scientists to refine the rotation period, identify any variations that suggest wobbling or precession, and possibly even correlate specific brightness features with surface regions. If there are localized areas of higher or lower reflectivity, maybe ice patches, dust deposits, or exposed rock, those will show up as recurring patterns in the brightness curve. And then there are the spectroscopic observations, which are arguably the most scientifically valuable. Every time a telescope captures light from the comet and splits it into a spectrum, it's reading the chemical composition of the coma. Different molecules absorb and emit light at different wavelengths, creating a unique fingerprint that tells you what's present and in what quantities. During the Earth passage, spectroscopy revealed water vapour, carbon monoxide, and traces of other compounds. During the Jupiter encounter, we'll get much more detailed spectra because the comet will be closer and the observing conditions will be better. Scientists are particularly interested in looking for rare or unexpected molecules, things like formaldehyde, methanol, ethane, complex organics. The presence or absence of these compounds tells us about the environment where the comet formed, the temperature and pressure conditions in the disk of gas and dust around another star billions of years ago. There's also the possibility of detecting changes in the comet's magnetic field, though this is a long shot. Comets carry weak magnetic fields embedded in the ionized gas of their comas, and when those fields interact with a planet's magnetosphere, there can be detectable effects. Jupiter's magnetosphere is enormous, extending millions of kilometers into space, and it's one of the most dynamic magnetic environments in the solar system. If 3i Atlas passes through it, instruments on Juno or on ground-based radio telescopes might detect transient signals, brief fluctuations in radio emissions or magnetic field strength that indicate the comet's plasma tail is interacting with Jupiter's magnetic field lines. It would be a subtle effect, difficult to measure and easy to miss, but if it's there, it's one more piece of the puzzle. Now let's talk about what could go wrong, because space observation is never guaranteed. Weather is the most mundane but persistent problem. If it's cloudy at the major observatories during the critical days, ground-based observations are scrubbed. There are backup sites and contingency plans, but you can't control the weather. Space telescopes don't have that problem, but they have their own constraints. Telescope time is allocated months in advance, and shifting schedules to accommodate last-minute observations is difficult. There's also the question of whether the comet will cooperate. If it's fainter than predicted, if the outgassing shuts down, if there's a dust event that obscures the nucleus, the quality of observations drops. Astronomy is full of variables you can't control, and every observation campaign is a race against time, weather, and luck. But here's the thing, even if we don't get perfect data, even if some observations fail or come back noisy, we're still going to learn. The sheer number of instruments pointed at this comet during the Jupiter encounter means that even partial success will yield a dataset richer than anything we've had for previous interstellar objects. Oumuamua was gone before we fully realized what it was. Borisov gave us more time, but it never came close to a major planet. 3i Atlas is giving us both time and proximity, and that combination is rare. The data that comes out of March 2026 will be studied for years. Papers will be written, models will be updated, and our understanding of interstellar comets will take a leap forward. And then there's the public engagement angle, which matters more than you might think. Space science isn't just for scientists. It's for anyone who's ever looked up and wondered. Events like the Jupiter encounter capture imaginations because they're happening now, in real time, and the outcome isn't predetermined. You don't need a PhD to understand that something from another star is passing through our solar system, and we're watching it happen. You don't need advanced math to grasp that this is rare and important. And when the images start coming in, when we see the first high-resolution shots of 3i Atlas against Jupiter's cloud bands, or the first spectroscopic data showing unexpected molecules, people will pay attention. That attention translates into support for space exploration, into funding for future missions, into the next generation of scientists deciding that this is the field they want to work in. So March isn't just a date on the calendar, it's a milestone, a convergence of technology, curiosity, and cosmic timing. It's the moment when years of tracking, planning, and preparation pay off in a burst of data that will reshape what we know, and it's coming soon, not years from now, not decades, weeks. The countdown is real, the stakes are high, and the universe isn't going to wait for us to be ready. It's happening whether we're prepared or not, and we are as prepared as we can be. Now we wait, we watch, and we see what 3i Atlas reveals when it meets Jupiter. Every encounter has an ending. When 3i Atlas makes its closest approach to Jupiter in March and then begins moving away, that's not the end of the story, but it is the end of a chapter. The comet won't stop moving just because we've finished observing it. It will continue on its trajectory, shaped by Jupiter's gravity into a slightly different path than the one it came in on, and it will head back toward the outer edges of the solar system. Eventually, it will cross beyond the orbit of Neptune, beyond the Kuiper belt, and into the space between stars where it came from. At some point, it will become too faint and too distant for even our best telescopes to track, and when that happens, when we lose sight of it for the last time, it will be gone from human awareness, continuing its journey through the galaxy toward a destination none of us will ever know. But before that happens, there's a period of observation after Jupiter that's almost as important as the encounter itself. Scientists will be watching the comet's outgoing trajectory, measuring how much Jupiter changed its path and speed, confirming the mass calculations, and looking for any delayed effects from the gravitational interaction. Sometimes comets exhibit changes hours or days after a close encounter, as internal stress from tidal forces causes delayed fractures or outbursts. If 3i Atlas does that, we'll want to see it, because it will tell us about the structural properties of the nucleus, how cohesive it is, whether it's a single solid object or a loosely bound pile of fragments. There's also the question of how long we'll be able to observe it at all. The farther the comet gets from the Sun, the fainter it becomes, both because of increased distance and because solar heating drops off, reducing outgassing and the size of the coma. At some point, the comet will fade below the detection threshold of most telescopes. The largest ground-based observatories might track it for a few more months, maybe into the summer, but by late 2026, it will likely be gone from view. That's just the reality of observing faint objects at interplanetary distances. Once it's beyond a certain point, we're blind. The comet will still be out there, moving through the darkness, but we won't be able to see it. So what happens to all the data we've collected? This is where the long-term value of the Jupiter encounter becomes clear. The observations made during March and during the months leading up to and following that encounter will form the most comprehensive dataset we've ever had for an interstellar object. That data will be archived, made available to researchers worldwide, and analysed for years to come. Some of the most important insights might not emerge until months or even years after the encounter, as scientists compare different datasets, refine models, and test hypotheses. The immediate observations tell us what happened. The long-term analysis tells us what it means, and what it means is that we're getting better at this. Each interstellar object we observe teaches us more about how to observe the next one. When one caught us off guard, we identified it after it had already passed closest approach to the Sun, and by the time we realised what we were looking at, it was fading fast. We learned from that. When Borisov came through, we were ready. We identified it earlier, tracked it more carefully, and got better data. With 3i Atlas, we're taking that preparation to the next level. We're coordinating multiple spacecraft, planning observation campaigns months in advance, and using every tool at our disposal to extract the maximum science from this opportunity. The lessons learned here will shape how we respond to the next interstellar visitor and the one after that, because there will be a next one. Statistically, we now know that interstellar objects pass through the inner solar system relatively frequently, perhaps 1 or 2 per year, that are bright enough to detect with current technology. The problem is that most of them go unnoticed because our sky surveys aren't comprehensive enough yet. But that's changing. New telescopes are coming online, like the Vera Rubin Observatory, which will survey the entire visible sky every few nights, catching transient events and moving objects that previous surveys would have missed. As our detection capabilities improve, we'll find more interstellar visitors, and each one will add to our understanding. There's also serious discussion happening now about future missions designed specifically to intercept interstellar objects. The idea is to have a spacecraft on standby, ready to launch on short notice when a new interstellar object is detected. The spacecraft would catch up to the object while it's still in the inner solar system, match its velocity and fly alongside it, imaging it up close, measuring its composition, maybe even landing on it or collecting samples. It sounds like science fiction, but the technology is within reach. The challenge is funding and political will. Space missions take years to plan and build, and they're expensive. Convincing governments or space agencies to invest in a mission to intercept something we haven't even detected yet is a tough sell. But 3i Atlas might help make that case. The more we learn about these objects, the more we realise how scientifically valuable they are, and the stronger the argument becomes for dedicated missions. Imagine a future where we don't just passively observe interstellar visitors from a distance, but actively send spacecraft to meet them, to escort them through the solar system, to study them in detail. Imagine landing a probe on an interstellar comet and analysing its surface composition, drilling into the ice, maybe even detecting organic molecules that tell us about the chemistry of other star systems. That's not decades away. That's something that could happen within the next 10 or 15 years if we commit to it. And the data we're gathering from 3i Atlas right now is part of building the foundation for those future missions. But let's zoom out even further. What does all this mean for our understanding of the universe? Interstellar objects are more than just curiosities. They're windows into environments we can't reach, messengers from distant places carrying information encoded in their composition, structure, and behaviour. Every interstellar comet is a sample of another star's planetary system, a piece of the puzzle of how planets form, how solar systems evolve, how common the building blocks of life are across the galaxy. When we study 3i Atlas, we're not just studying one object. We're learning about the processes that shape planetary systems everywhere, and there's a deeper question lurking beneath all of this, one that we haven't talked about directly, but that's always present in the background when we discuss interstellar visitors. Are we alone? Is life common in the universe, or is it rare? Are there other civilizations out there, building telescopes of their own, watching their skies, wondering the same things we're wondering? Interstellar objects don't answer that question directly, but they're part of the search. If we ever find clear evidence that an interstellar object is artificial, a probe, a derelict spacecraft, anything that can't be explained by natural processes, it would be the most profound discovery in human history. We're not there yet. 3i Atlas shows no definitive signs of being anything other than a comet. But the fact that we're taking the question seriously, that we're looking carefully and keeping an open mind, is important. Science advances when we're willing to ask difficult questions and let the evidence guide us. So what comes after Jupiter? More observation, more analysis, more questions, and hopefully more answers. The March encounter is the climax of this particular story, but it's not the conclusion. The conclusion comes when we've wrung every last bit of insight from the data, when we've updated our models and refined our understanding, when we've taken what we learned and applied it to the next challenge, and the next challenge is already on the horizon. The next interstellar visitor is out there somewhere, maybe already on its way toward the sun, maybe still years away from detection, but when it comes, we'll be ready. We'll be better prepared, better equipped, and better informed because of 3i Atlas. And in the meantime, we have March. We have a few weeks of anticipation, of watching the skies, of waiting to see what this visitor from another star will reveal when it meets the giant of our own solar system. If that doesn't excite you, if that doesn't make you feel connected to something larger than yourself, then I don't know what will. This is humanity at its best, curious, collaborative, reaching out into the universe with our instruments and our minds, trying to understand the cosmos we find ourselves in. So stay tuned, follow the updates, watch for the images and the data as they come in. This is happening now, it's real, and you're part of the audience for one of the most extraordinary astronomical events of this decade. Hit that subscribe button so you don't miss the March coverage when the encounter happens, drop a comment and let me know what aspect of this story you're most excited about, and share this with anyone you know who loves space, who looks up at the night sky and feels that sense of wonder. Because this is a story worth sharing, and it's a moment worth witnessing together. We're watching something from another star pass through our solar system, and in a few short weeks, we're going to see it closer than we ever have before. The universe is vast, mysterious, and full of surprises, and 3i Atlas is proof that sometimes those surprises come to us. All we have to do is pay attention.